In this video, we're looking at astronomy, and in particular, we're looking at various topics to practice and study and revise for a test on astronomy on certain topics. These topics are ancient astronomy, the geocentric and heliocentric models, solar system, planetary motion, the sun, nuclear fusion, life cycle of a star, galaxies, space and universe, and the Big Bang. So generally covering the introduction to astronomy at the high school level. And this is a review video to look at each part in detail. Science classroom. So ancient astronomy refers to Greece, or ancient Greece. Now ancient Greece used or came aware of certain theories and ideas of astronomy and space and science and philosophy based on other cultures in previous, like the Egyptians. But the ancient Greeks, they really propelled the ideas and philosophies and theories of this science, astronomy, to new heights. And certain people were credited with doing this. So Aristotle was the first real famous thinker of Greece that kind of pushed the idea that the Earth is in the center of the universe, that the orbits were circular and very heavenly, and that using epicycles could explain how the planets moved. And even the word planet means wanderer. Then we have Aristotle, who worked on the circumference of the Earth and figured out how wide and big the Earth is to a 4% error back in 240 BC using angles of the sun and shadows on the Earth's surface. Then we had Ptolemy, who kind of cemented the geocentric model for the Greeks and the understanding of how the system worked in 100 AD, using a total of 55 epicycles to explain the loops and movements of planets around the Earth. The Greeks finalized their model, or their understanding of how the solar system works, putting the Earth in the center as not just a planet, but the center that everything rolls around. So other planets like Mercury, Venus, and Saturn, and the Sun, obviously the Moon, would revolve and orbit around the Earth, being that humans are the most important part of the whole system. Now this was really confirmed by the Ptolemaic model, Ptolemy in 100 AD, whereby he used all the epicycles and really finalized this, in their mind, conclusive model of how the system works. Now this would stand or be understood or believed or worked with for about 1400 years, because the Catholic Church, when it emerged through the ages, since ancient Greece kind of diminished as a society, the Catholic Church and the Pope and the Vatican really did propel and agree upon and want to push this idea that the Earth's in the center and that man was the most important thing. So the Catholic Church kind of pushed this idea for a long time and inhibited any other scientists coming out with other contradicting ideas that would disprove this geocentric model. So one of those natural phenomena that the ancient Greeks observed in space of these planets and how they move across the night sky over a period of time was retrograde motion. Now retro means backwards or delayed. Grade means the amount or the extent of what's happening, and motion means obviously the movement across the sky, the night sky. So planets appeared to move backwards at certain times according to what we're looking at on Earth. So this is an apparent motion. This is a motion that we see on Earth that is not really happening, but because of our position or our perspective, this is what's happening. So the main planet we observed was Mars, and how Mars every 2.1 years would go through this retrograde motion whereby it would move backwards against Earth's movement for a period of months. So rather than going east, it would go west for a few months and then come back east and create this loop, this retrograde loop. And ancient Greeks saw it and prograde motion, but it was not explained, but that's why they used epicycles in the geocentric model to account for this natural phenomena. And it only happened, or only was proved, when Copernicus came around and then started what's called the heliocentric model. Nicholas Copernicus, a Polish monk born in 1473, studied astronomy and different subjects in university in both Italy and Poland, was very enthusiastic about astronomy and reading papers about planetary motion that were going against the very well-known and cemented geocentric model from the ancient Greeks. And of course, the Catholic Church liked it, so no one really spoke out in fear of their death. So Copernicus was the same. On his deathbed in 1543, he actually allowed his book, his new Origins of Planetary Motion, to be published. And this put the sun in the center. This was revolutionary because it was not done before. And it became the heliocentric model. Helio means sun, centric means centered. And putting the sun in the center would organize the planets in a way that had not been done before, that made a lot of sense, and would actually prove a lot of the geocentric model issues and problems to be, wrong, and this model, this sun in the center, is correct. So Copernicus was accredited with this new idea, which kind of sprung the scientific revolution, which went from 1543 to 1642, about 100 years. And this included people like Newton and Kepler and Brahe and Galileo and Shakespeare and Rembrandt and Michelangelo. Once the sun was put in the center by Copernicus in a heliocentric model, these other scientists moving forward could work with this and then do a much better experiments and understanding and put math into the motion of planets around the sun and how they orbit and revolve. And all this new work was being done and published. And Brahe was an astronomer scientist in Denmark with his own observatory, and he observed the motion of planets for about 20 years. A great, massive amount of detail and accuracy went into his work. And then he hired Kepler, a German guy that came up, young guy that came up and worked with Brahe, and he worked on Mars. And Kepler then formulated his 3 laws of planetary motion. First law, second law came in 1609, the third law in 1619. And they basically explained how the orbits are elliptical, not circular, and that the law of equal areas in terms of the speed at which the planet moves, at the aphelion and perihelion, if it's close or far away from the sun. And the third law was based on the law of harmonies, which was basically saying that all the planets' distance is also related to the speed of orbit, which infers gravity before Newton worked with it. Then you had Galileo in 1610 using his telescope to see the four moons of Jupiter, Ganymede, Io, Callista, and Europa, looked at Venus's phases, the sunspots, and the craters on the moon. So he pushed on, these 3 people pushed on astronomy to great heights once Copernicus put the sun in the center and everything was allowed to be worked with, and the Catholic Church kind of lost their grip on the geocentric model. So after the 3 chaps, Brahe, Kepler, and Galileo, kind of propelled astronomy through to the new revolutions and discoveries, Newton came around, who was a mathematician in Cambridge, very smart gentleman, and worked with the idea that there was a force that was used for attraction between objects and mass, and this was called the laws of physics, or Newtonian physics. And he had 3 laws based on the gravity or the force on Earth, which was the law of inertia or motion, law of acceleration, and law of reactions. And these 3 were done first in 1686 and published completely in 1687. And his 4th law applies to astronomy outside of Earth, the gravity between masses in the heavenly bodies, and this was the universal gravitational attraction law, and how masses of different sizes would have different amounts of gravity, and the force between them would vary based on the distance and the size of each mass. Since the scientific revolution occurred, the acknowledgement and understanding of our solar system keeps growing every day. Now, the telescope was invented in 1608, not by Galileo, but by a gentleman in the Netherlands. Now, Galileo was famous for observing certain parts of the solar system, like the Galilean moons of Jupiter in 1610, but he didn't invent the telescope. However, our solar system, with the use of the telescope, was able to document and see different planets, different characteristics and components of our system to understand it in greater detail. So we have these 2 sets of planets, terrestrial and Jovian. Terrestrial, there are 4 planets that are closest to the Sun. They are Mercury, Venus, Earth, and Mars, and they are rocky bodies. They are smaller, they have less moons, they are faster orbital periods around the Sun, generally hotter, and various ranges of atmospheres. Earth has a moon, and Mars has 2 moons. Then you get the Jovian planets. This is past the asteroid belt, which is the leftover rocks from the formation of the solar system. The Jovian planets are gas giants, and the 2 biggest ones in the first part are Jupiter and Saturn, and then the last 2 are ice giants, which are Neptune and Uranus. Now, these planets are very large. They have mostly a gas outer exterior, which do have a rocky core, but most of it is gas, and the gas is hydrogen and helium, certain levels of ammonium and methane. and they are lighter. They are huge planets compared to the terrestrial planets. They have way more natural satellites, and they're colder, and they have longer orbital periods around the Sun. So there's distinct differences between these two types of planets, but each planet has their own characteristics. For example, Mercury is the closest, but not the hottest. Venus is the hottest with the biggest atmosphere. Earth is the perfect place for organic life, thankfully. Mars used to have life, maybe, and water and an atmosphere, but now doesn't, and it's a red planet based on the iron oxide in the soil. Jupiter is the largest gas giant, and it has 95 moons and a ring system, and the 4 biggest are the Galilean moons that were saw by Galileo in 1610. Then you have Saturn with a ring system, the beautiful ring system, 7 divisions, and it has 124 moons. The biggest one is Titan. Then you have Uranus and Neptune, both ice giants, both blue in color due to the methane in the atmosphere, so they are also named after Greek gods, but Uranus smells like farts. Hilarious. So our solar system is more than just the 8 planets. It's to do with the minor components of the system in terms of what's held by the sun's gravity. The sun is so massive compared to the other parts of the solar system that it's 99% of the mass. So the gravity obviously follows along with the mass, and the gravity controls all the movements of the planets and distance and orbital period. So in terms of the minor components, you have all of the asteroid belt, Kuiper belt, and Oort cloud. Kuiper belt is that exterior layer that's past Neptune that includes Pluto as a dwarf planet and other dwarf planets. And then the Oort cloud is the far exterior, the furthest extent of the sun's gravity, where you have the icy pieces of rock and kind of exterior shell of our system. So past the Oort cloud, you're into the space between stars, which is interstellar space. So the other parts of the components of the solar system would be the ring systems, the dwarf planets like Ceres and Pluto, and other components like comets as well, long and short comets that are going to orbit around our star. The sun, or our star, is an amazing component of our solar system. It wouldn't be a system without the sun. So it is a giant ball of plasma and gas that's a nuclear explosion in space, releasing energy to all areas of space and received by the planets. And this energy is in the EM spectrum. Now, the energy derives from the sun's core, which is under immense temperature and pressure of 50 million degrees and exponential pressure, which causes nuclear fusion to occur in the core, which is the fusion of these protons towards each other and together to create, from hydrogen, which is the one proton, to helium. And when the process of forming helium, you're releasing particles and also energy. This energy is then transmitted through the core, out of the core, out to the exterior of the sun, through different layers, and into space. The layers of the sun go from the core to the radiative zone, to the convective zone, out to the surface somewhat, which is the photosphere and chromosphere. Photosphere is the light layer, thin, allows light to go through. Chromosphere is color, appears the yellow color based on the size and energy and luminosity of the star, and then goes into the corona, which is the atmosphere of the sun, and then it can go into the far reaches of the atmosphere in terms of solar flares, prominences, and coronal mass ejections. Again, it's the pushing out of this energy and electric charges from the sun into space. Now, the sun is 4.6 billion years old. It started as a stellar nebula, condensed, fusion started. It happened, the sun now is basically in its main sequence stage of its life, and then it will turn into a red giant when the hydrogen is exhausted in the core, and then it will implode into a planetary nebula and turn into a white dwarf. So our sun is a star, and looking at other stars around the Milky Way galaxy basically showed us the potential for our sun and what's going to do based on the size and the amount of energy and the spectrum that the sun gives off compared to other stars. So our characteristics of stars are based on one thing. It's the mass, how big the star is, and that is dependent on how much stellar nebula is used to form the star in terms of the collapsing and the formation of the core and nuclear fusion. Once this happens, it is then a main sequence star, which is where the star spends most of its life and what we find most of the stars are in, about 90%. At the end of the star's life, it depends on the size, so the small and medium-sized stars will go into a red giant and expand based on the lack of hydrogen, and then it will basically implode and dissolve into planetary nebula, and then the core is left to cool down. This is called a white dwarf, and it's very small. It's like the skeleton of that star. Then if you have a big mass star or a high mass star, it will turn into a red supergiant in its later stages of its development, and then it will go into a large explosion called a supernova, and that supernova will either turn into a neutron star, which is a very small, high dense leftover part of the star, or it'll go into a black hole which will implode in itself and form black holes, which we now know are in the center of every galaxy. In addition to the life cycle of a star, other astronomers were looking at different stars in the night sky, stars that were close or far away, and they started to analyze the characteristics of those stars and the light they were receiving through a telescope. Characteristics like the absolute magnitude, the surface or effective temperature in Kelvin or Celsius, the luminosity, and the spectral class. Now, the absolute magnitude is the brightness, the absolute brightness based on a clear comparison of what is bright, what is not bright, or dim and bright. Then surface temperature, which dictates the color of the star, is the surface temperature, and then the luminosity is the energy, which again refers to the temperature and has a direct link with the absolute magnitude. And finally, the spectral class. Spectral class has links referring to the temperature and the color of that star. So this graph was actually formulated by two different astronomers, Russell and Hertzsprung. Russell did it in 1913, his combination of characteristics, and so did Hertzsprung, but in 1911, and they combined these data sets to create this awesome graph, the HR diagram, and you can analyze all the different types of stars and their different life cycles based on their characteristics, and it looks like this, with the main sequence being the majority of the graph, going from right to left, and very range of luminosity, a range of temperature, range of class, and obviously magnitude. Then you have the blue giants, the white dwarfs, the red giants, and red supergiants, again with their own characteristics can fit on the graph. And the X marks the spot, that's our sun. So leading on from the individual star and the characteristics and how we can compare different stars based on the HR diagram and based on the life cycle, based on their mass and how they're going to be born and how they're going to die in different ways, which create awesome, spectacular phenomena in astronomy, is the collection of stars. And the collection of stars in the hundreds or tens or thousands of millions are called galaxies. Now, galaxy is a Greek word that comes from galax, which means milky, and William Herschel first looked at the Milky Way in detail in 1783 with his telescope, and from there in 1920 we understood that galaxies are a collection of stars under gravity, or the force of gravity, and how the universe is this large entity that contains all these galaxies and all these stars in various clusters and supergroups and local groups, and how the whole system is one big entity which is still unknown to a certain fact of what controls it and what is behind it, the energy that we can't always see that's binding between galaxies and how they function. But we know that it's around 13.8 billion years old, and the galaxies that we're looking at through Edwin Hubble, were mostly spiral. So about 60% of the galaxies are spiral, which includes regular spiral and barred spiral. And the level of closeness of each of the spiral arms is dictated by the A, B, and C. A being nice and close spiral arms, and C being the further away and spread out, again based on gravity. Then we have 20% which is lenticular, which looks like the lens of an eye, 15% elliptical, and 5% irregular. So these are the types of galaxies that we've observed through telescopes, through the Hubble telescope and through land-based telescopes. The origin of our universe is still controversial and still up for grabs in terms of a conclusive theory. However, the most common, the most used theory is the Big Bang theory. This is an idea or a theory that suggests that the universe was once a singular point in some sort of space and had an exponential explosion, bang, so to speak, and all the elements, mass, materials were suddenly expedited into space, into the universe, and it grew from there and has been growing and increasing in size and spreading out ever since. So this theory has been supported by many scientists, and there are some alternative theories out there on how things started. And really one of the main bits of evidence was from Christian Doppler in 1842 that looked at the frequency of sound waves in Austria and concluded that when you stretch the sound wave and the frequency, it changes its pitch, its frequency. And then Edwin Hubble in 1929 suggested that if you do the same thing with light energy, light waves, which work the same way as sound waves but a lot faster, that you can change the frequency and the wavelength of that energy and it will change the color. So if you stretch out the wavelength, it will turn into the red spectrum of the visible light of the EM field or EM spectrum, and then if you actually squeeze and compress the energy, it will go to more blue, just like the rainbow, red on one side, blue on the other side. So this was called Hubble's law, and when he looked through the telescope at distant stars at different areas of space, he noticed that the majority of them appeared red. So the energy from that star that is being received by the telescope that Hubble's looking through was being stretched and appeared red versus blue. So if all those appeared red in all different directions, he had the conclusion that the universe was expanding, and that was the first piece of evidence to support the Big Bang Theory. A second piece was the acknowledgement in 1967 of background cosmic radiation and how it's changing of dark energy, and also the cooling of the universe and how the different elements that make up the universe are cooling down, and how the observation of older stars has a different composition of elements versus the newer stars. So these pieces of evidence support the Big Bang Theory. However, this is not confirmed, and in terms of the existence of black holes and Hawking radiation and what a black hole is, which is formed from the collapse of a very large star after a supernova in certain conditions. And we now know there's black holes in the center of different galaxies, and how the black hole functions and changes and warps and twists time and space and what happens through it. Again, it's all theories and just requiring more research, more observation, and more time to figure out what these amazing phenomena and the origins of our universe are or is.